Hi, Chelsy. How are you doing?
Hi, sir. I'm good. How are you?
Very good. Very good. So, how is your Christmas going on?
It's good. It's nice to have a winter break right now.
So true, right? Sub-zero temperatures outside and at home with family. Nothing could be better than that, correct? So, tell me, today, what do you want to do in mathematics?
So today I wanted to go over two chapters about logarithms from the Nelson textbook, 8.3, evaluating logarithms, and then laws of logarithms.
Okay, both the chapters. Great. So, we'll have
Mhm.
to go slightly faster. Are you ready for that?
Okay, yeah.
Okay, then share the screen and
Yeah.
then we'll go through it.
Mhm.
And wherever you have any difficulty in understanding, just stop me, right? And then we'll look over it. So don't hesitate. Great. So evaluating logarithms. So example number one, 2187 equals to 3 to the power of something. So we have to find that power, right? So let's look into how do we solve such a question, right? Without getting into details, you can always read the examples. So we have 2187 equals to 3 to the power of t plus 1, correct? Now, one way is that you could write 2187 as 3 to the power of something. You could do that, correct?
Yeah.
So do you know 3 to the power of what could be 2187? Is it a multiple of 3? So when you
Mm,
add them, you get 2 plus 1 plus 8. You see 2 plus 1 plus 8 plus 7 is how much? 18, right?
mhm.
It is a multiple of 3. So we could write this as power of 3, correct?
Oh,
Yes.
okay.
Right. So let's write down powers of 3. So 3, and then when you multiply by 3, what do you get? 9 times 3, 27 times 3, 7 times 3, 21, and 2, 81 times 3, 243 times 3, 9, 3 times 4, 12, 2, 1 carry, 729 times 3, 9 times 3, 27, 2, 3 times 2, 6 and 2, 8, and 21. So, oh, sorry, 27, sorry. 9 times 3, 27, 7, 2187. So we get the power. Do you see that? So this is to the power of 1. This is to the power of 2. This was to the power of 3, 4, 5, 6, 3 to the power of 7. Is that clear?
Yeah.
So we have 3 to the power of 7 equals to 3 to the power of t plus 1. What do you notice? We have same base, correct?
Mhm.
So left side is equal to right side with same base means exponent should be equal, correct? So 7, the exponent of 3 on one side should be equal to t plus 1 on the other side, right? T to the power of 7 equals to t to the power of, 3 to the power of 7 equals to 3 to the power of t plus 1. They should be equal. Find the value of t. Rearrange. Correct?
Yeah.
So that is how you can actually get this answer. So the idea here is, if you are given a number and the base on the other side, figure out if it is a multiple with that base. In that case, you can actually solve as we solved just now, correct?
Mhm.
But can you do this for all the numbers? For example, let me take another question. I'm writing 10 equals to 2 to the power of x. Now, can you tell me what x is? We don't know. How can we solve this? Now let's look into this. So we have this equation. What did I say? 2 to the power of x is equals to 10. Find x. We know logarithms are inverse of exponential functions, right? So we have to take log both sides. Is that okay? Now, logs on calculator are given to the base 10 or to the base e. So we'll use to the base 10. Is it okay? So we are given the equation is 2 to the power of x is equals to 10. So we can take log on both sides. We get log of 2 to the power of x equals to log of 10. Now, it is an important property also. When the base and the number argument is same, the value is 1. And here, we could write this log to the base 10, 2 to the power of x as x times log 2. And that is 1. And from here, we get x equals to 1 over log 2. So you can use the calculator, calculate this value to get the answer. You get the idea.
How did you get equals 1?
Okay, very important. Use your calculator. Check what is log 10.
1.
1. See, now let us look at it. So when I write log to the base 10 of 10, let us say it is equal to some number n. Is it okay? Can you write this in exponential form? It will be 10 equals to 10 to the power of n. This is writing it in exponential form, correct?
Yeah.
On the left side, we have 10, which is 10 to the power of 1. So that means 1 is equal to n. You see that? So we can write log to the base 10 of 10 equals to 1.
Okay.
Clear? Great.
Yeah.
So I'll clear the screen. Let's move on to the next example. Okay, what does it say? It says, yeah, can you read the question, please?
Example 2, yeah. Using reasoning to evaluate logarithmic expressions, use the definition of a logarithm to determine the value of each expression.
Correct. So it says, use the definition of logarithms to determine the value of each expression. Let's begin with the very first one, which is log to the base of very small, 4, right?
Yeah.
Of 64, correct? Now, we don't know what this is. So what we can say, let this be some number n, correct? Now, when we say definition, that means now we want to write this log function as exponential functions, right? Equivalent. So how can you write this as an exponential functions? Base is 4. So base remains same. So we get 64 equals to the base of 4 to the power of n, correct? Can you write 64 as a power of 4? 4 times 4 times 4, 4 cubed, right? And therefore, I can write 3 equals to n. Do you see that? And that means log to the base 4 of 64 is equal to 3. Is that clear to you?
Yes. Yeah.
Okay. Now, the next one here is log 2. I'm doing part C for you. And we have minus 4. In that case, can we find the value of this function?
Yes.
How?
By doing the same thing, by using...
Okay, let's write n. Let's write n. So we get minus 4 equals to 2 to the power of n. Can 2 to the power of n be negative?
No.
No. So this is not in the domain. So in this case, not in domains, right? No solution. Is that clear?
Yeah.
So if you recall, as far as the logarithmic functions are concerned, the graph of logarithmic function to the base greater than 1 is something like this, right? Is it clear? So we know that x value has to be greater than 0. Now in this case, it was negative, and therefore it has no solution.
Oh, okay.
If you see it from the other side, for an exponential function, we know the graph is always positive, right? It could be like this or like this, right? It is never negative. And therefore, the inverse will not exist for a negative value. Does it make sense to you?
Yeah.
Great. So we'll move on to the next example. Can you please read the question?
Determine the approximate value of log 5 to 47.
Okay, so we need log to the base 5 of 47. Let us say approximate value is n. That means 47 is 5 to the power of n, correct?
Yes.
Now, 5 to the power of something. What are the powers of 5? Let us check. So 5 to the power of 1 is 5. 5 to the power of 2 is 25. And 5 to the power of 3 is 125, correct?
Mm-hmm.
Now, how do you get the 47?
You know it has to be between 2 and 3.
Yeah, it has to be between 2 and 3. So you can estimate, correct? You can apply calculator and do it, right? So you can estimate. Is it okay?
Yeah, so how would you go about estimating the number? Like what would you
Just
do?
use calculator. Do 5 to the power of 2.3, let us say. What do you get?
Okay. Yeah, 40.5.
So lesser. So 5 to the power of 2.4 is how much?
47.5.
Not bad. So slightly higher. 5 to the power of 2.39. One decimal place.
Five to the power of 39.
5 to the power of 2.39.
46.8, to which you could round to 47.
Okay. So 5 to the power of 2.395. Oh, sorry, 395 I have read. Let's see. 5 to the power of 2.395. Calculate this one.
47.2.
Very close, right? Like
Yeah.
this, you could calculate
Okay.
estimating. You get the idea, right?
Yeah.
And logarithms will give you exact answer. Let's find the exact answer for this. I could take the log value. So log of both sides, log of 47 will basically n times log of 5, right? So n is equals to the ratio of log 47 and log 5. Can you calculate this? What do you get?
2.39. 392.
392. Do you see that? So that is how you could find all very much closer than what we found, but we were close enough. You get the idea, correct?
Yeah. So what you did was you
Yeah, starting from there, estimated the two extremes and then in between, right? We averaged it out, kind of. Is that clear to you?
Yeah, and then on the left side, what you did was log 47, and then
Yeah, we took log both sides and then calculate. Is that clear to you?
uh,
The properties of-
5. Okay.
Can you tell me the answers for each?
Log 6.1. So what you have to do first is 1 equals 6 to the power of n, right?
Okay.
And then you have to find what n is.
Yes.
But then nothing equals 1. Like, how do you find 1?
Zero, right?
Oh,
Six
okay.
to the power of 0 is 1. And therefore, you'll see always when you sketch a logarithmic function, at 1, the value of y will be 0. Is it okay? Makes sense, right?
Okay.
Because
Yeah.
anything, any number a to the power of 0 is equal to 1, provided a is not equal to 0, correct? So remember this property. So this example is based on the laws or properties of logarithms. Clear?
Yeah.
So first one, we got this. Now next one, log to the base 5 or 5 to the power of x. What is that equal to? We have used this property, it is equal to x, correct? Let us do it. If you say that this is equal to 1. Let us say x. So let us say this is log to the base 5, 5 to the power of x is equal to y, let us say, right? If I write in exponential form, what will I get? I get 5 to the power of x is equal to 5 to the power of y, and clearly x is equal to y. Is it okay? So y is equal to x, correct?
Yeah.
So that is how we get the formula that log to the base b of a to the power of x is basically equal to, if I write a as b, then it is equal to x. Is that clear to you? Same base.
Okay.
Makes sense, right? Because if I write in exponential form, I get b to the power of x is b to the power of x. That's always correct, correct?
Okay.
Next example. 6 log to the base. What is the base there?
It's so small. I can't.
Yeah, must be 6. Okay, must be 6.
Okay.
And that should be equal to x itself. Okay, because it is inverse of one another. Exponent and logarithms are inverse functions. That is why. Is that clear to you? Okay, enlarge this. Move the screen up, enlarge, and then we'll go through the solution.
I don't think I can enlarge. Hold on.
Yeah, yeah. See now. 6 to the power of log to the base 6 of x, let it be equal to y, as we had been doing, right? Now, you can take log, you can write this logarithms as log to the base 6, right? So we can write this as exponent, which is log 6x is equal to log of 6x, correct?
But then what happened to the y? Oh, the y equals x?
No. The thing is that the left side is equal to the right side only if x and y are equal. Do you see that this is never equal unless and until x and y are equal, correct?
Yeah.
Only if they are equal, then you get, and that is why we have 6 to the power of log 6x is equal to x.
Oh, okay. Because the y has to be the same thing as x.
Yes. Otherwise, they're not equal. Is it okay? Correct. Okay, now let's move on to the exercise. Okay, read the summary.
Yeah, I can read it. Key ideas. Simple exponential equations can be solved using a variety of strategies. Expressing both sides as powers with a common base and then equating the exponents. Graphing both sides of the equation using graphing technology and then determining the points of intersection. Rewriting the equation in logarithmic form and simplifying. A logarithm is an exponent. The logarithm of a number to a given base is the exponent to which the base must be raised to get the number.
Right. Need to know.
Logarithms of negative numbers do not exist because a negative number cannot be written as a power of a positive base.
Correct.
A logarithm written with any base can be estimated with a calculator using graphic technology or guess and check.
Correct.
The expression log x is called a common logarithm. It means log base 10x, and it can be evaluated using the log key on a calculator.
Correct.
The following are some properties of logarithms where a is greater than 0 and a cannot be 1. So log base a1 equals 0, log a to ax equals x, and a log a to x is x.
Because these are inverse functions, okay? So they cancel out. Is that okay? And so you get x. Is that clear to you?
Yeah.
Let's go through the exercise. Take up questions one by one.
Okay.
Let's begin with some examples here. Express in logarithmic form, right? So if you have this one, can you tell me how will you write this as logarithmic form? Base is 4. Since the base is 4, we'll write log to the base 4 of this number 16 is 2. You could have also written as 2 equals to log to the base 4 of 6. Is that clear to you?
Yeah. Why is it 6, not 16?
Oh, sorry, 16. Sorry.
Oh,
16.
okay.
Good job. Now, D, can you tell me what should this be written as?
Wait one moment, sir. I just
Base is 6.
so always the base stays 4 for question A, right?
Yeah.
Okay. What?
So, minus 2 equals to log to the base 6 of that number. Is that clear?
Yeah.
Good. Let's clear this. Move on to the next question, which is expressed in exponential form. So the very first one, log to the base 2 of 8 equals to 3. Correct?
Yeah.
Just take the base on the other side, leave the numbers, right? Now let's do E part. Log to the base 6 of square root 6 equals to half. Exponential form. Do you see that?
Yeah, I'm a bit confused with this example.
So 6, take 6 on the other side. 6 to the power of half is square root x. Let's do one more. Let's do this. We have log to the base of 1 by 6 times 216 equals to minus 3. Base is 1 by 6, right? And 216 will leave 216 here itself. Base of 1 by 6 to the power of minus 3. Does it make sense?
Yes. Okay.
That is how you have to do it. Is that okay?
Mm-hmm.
Can you tell me solution of this one now? Evaluate. Log 7 square root 7 is equal to what? Let's say it's n. Then how will you find n? Tell me. Write it in exponential form. Square root 7 is equal to 7 to the power of n, correct?
Yeah.
Now, square root 7 means what? 7 to the power of half, right? That means n equals to half. So once you have the same base, compare the exponents.
So can you explain how you found the half again?
Square root 7 is what? Square root 7 means 7 to the power of half.
Okay.
Therefore, we get the answer. Is that okay? We'll do one more question. We have the question here as log to the base 2 of cube root of 2, right? So we have to evaluate. Evaluate means find the value of this. Let this be equal to x. How will you find x? So we'll say cross this. We have got cube root of 2 is equal to 2 to the power of x. This is 2 to the power of cube root means 1 over 3, right? Is 2 to the power of x. That means 1 over 3 is x, correct?
Yeah, okay.
That is how you. Perfect. Now let's move on. Take question number 4. Round your answer to 2 decimal places if necessary. Solve for x. Use calculator. That's simple, right? Can you do this one for me? Log x equals to minus 2. X is equal to 10 to the power of minus 2, which means 1 over 100. Correct?
Mm-hmm.
Because if nothing is given as the base, by default, it is always 10.
Yeah, okay.
Correct. Question number 6. Okay. Solve. Which one will you solve? Solve this D.
Why does it become 4? And like, why did you turn 1/4 to 4?
-2. The power was, exponent was -2. Minus means reciprocal, right? So 1/4 to the power of -2 is same as 4 to the power of 2. And 4 square is 16.
Okay.
Okay, question number 7. So that is using graph. We'll skip that part. All right. Estimate, you know how to estimate. We'll skip that part. Evaluate. Let's evaluate. So, okay, can you tell me answer for D? Log to the base m of m to the power of n is equal to what? Just n, right?
I don't understand.
The formula. Okay, right. Go back to the key formulas in the beginning. Write down the 3 formulas. Good. Yeah, wait. Copy these 3 formulas. Also copy one more formula which I'm writing for you here. Log to the base b of a equals to x in exponential form. This will be written as a equals to b to the power of x. Is it okay?
Mm-hmm. Do I go back to the question?
Yeah. Now you.
Oh, 2.
Okay, 8. Answer the first one. Log to the base 4 of 32. Estimate the value of each of the following logarithms to 2 decimal places. Let's estimate. Log to the base 4 of 32, right? Let it be equal to x. That means 32 is equals to 4 to the power of x, right? So the x value will be between what? We know 4 square is 16 and 4 cube is 64. So the value of 32 is somewhere in between, right?
Yeah.
So now use your calculator to find the value of 4 to the power of 2.5. Check middle value. 4 to the power of 2.5. What do you get?
32.
Perfect. You got 32 exact?
Mm-hmm.
Okay, great. So that becomes our answer. Okay.
So then, didn't earlier we did a question like this where you like divided the 2? Can we still do that here?
Now we got exact value. We wanted that value, right? Log 4 of 32. We wanted 32 only, right?
Yeah, but
So
like,
we got,
for example, we did a question earlier where it was the same thing, and we
yeah.
but
So
then
there the
like
value was not exact, so we had to approximate. You get the idea.
Yeah.
You see, if you think about it, 32 can be written as 2 to the power of 5, right?
Mm-hmm.
And we want that to be equals to 4 to the power of x, correct? But 4 can be written as 2 square, right? 4 can be written as 2 square. And therefore, 5 is equals to 2x and 5 divided by 2 is equals to x, which is 2.5. You see how we got the exact value and why?
Mm-hmm.
Because both 32 and 4 have a common base of 2. That is why.
Okay.
Correct. So let's evaluate question number 9. So can you tell me log to the base 3 of 3 to the power of 5 will be how much? Look into the properties.
So is it 5?
Correct. Next one. 4 to the power of log to the base 4 of 1 over 16 is equals to what?
One over 16.
Perfect. Next one. A to the power of log to the base a of b is equal to what?
I don't know this one. How do you do this?
B, because log a to the power of log a is inverse, right? Reciprocal, I mean inverse. So b is left. Use the formula. Just
Okay.
as previous one was 1 over 16, here b is 1 over 16 instead, we have b, right?
Okay.
Okay. 5 log to the base 5 of 25 is equal to what? Tell me.
25.
Next one.
N.
Next one. Log of 1 is always 0.
0. Right.
Correct. Anything to the power of 0 is done. Is that clear to you?
Yeah.
Correct. So we got all this. Now, let's do the next question 10, which is log to the base 2. Log to the base 2, 16 to the power of 1 over 3 is equal to what? Let it be x. Find x.
Oh, okay. I see what you did. Yeah.
Correct. So you get the concept, right?
Mhm.
Okay.
So what you did here was you had
Common base.
base and then the exponent on one side, and then you move the base 2 to the other side,
Yes.
and then you made the 16 have the same base as the other side.
Correct.
And then
So first thing, write in exponential form, right?
Mhm.
And then write in common base. And then equate exponents. So those are the steps to do such questions. Perfect.
Yeah.
Let's do question number 12. Yeah, move the screen up. Let's do question number 12. Can you read the?
Half-life is the time it takes for a half of a sample of a radioactive element to decay. The function m of t equals p of 1/2 t over h can be used to calculate the mass remaining if the half-life is h and the initial mass is p. A half-life of radium is 16,020 years. If a laboratory has 5 grams of radium, how much will there be in 150 years?
Just plug in T as 150 and calculate, right? So lab has 5 grams of radium. That means the value of P is given to you as 5 grams, right? And now you want to find the value when what it remains after 150 years. So when T is 150 years, substitute, get the answer. Because P, M of T can be used to calculate mass remaining. So the remaining mass is after 150, plug in 150 there, 5 grams starting, half to the power of 150 divided by half-life 1620. Use calculator. So first find half means 0.5 to the power of 150 Yeah, calculate, see how much you get.
So are we doing to the power of 150 divided by?
1620 in the exponent, yes.
Yeah, okay.
And multiply that by 5, correct? How much you get?
Yeah, same answer.
Correct. Now, second, how many years will it take until the lab has only 4 grams? How will you do that part? Part B, 4 grams is left. That means empty is given to you as 4, right? So we get 4 equals to 5 within brackets half of t divided by 1620. Now, how will you find t? So we'll first divide by 5. So get 4 over 5 equals to half to the power of t divided by 1620, correct?
Mhm.
Now we can take log on both the sides, correct? So we get log of 4 over 5 equals to t over 1620. That is properties of log of half, correct? So from here, we can find the value of t. So let me write down t as equal to cross multiply. So we get 1620 times log of 4 over 5 divided by log of half. Use calculator to calculate. You get the idea?
Yeah.
So you can use calculator and find this answer. So that will give you answer for part B. Is that clear?
Mhm.
Okay, so let's move on. Go further. Let's see how many questions are there in this. Okay. Okay, let's do extended questions. Now we've got this question which says 3 to the power of log 327 plus 10 to the power of log 10,000. We have to simplify this. Can you do this?
Uh,
Simple, right? 3 to the power of log 327 will be 27. 10 to the power of log 10,000 will be just 1,000. Add them up and you get 1027.
oh, okay.
Part B, can you do that? So 8 minus, now you got all this. So now there's a log property that if you do sum with the same base, they get multiplied. So this part here, you have not learned the properties, but it will be like log to the power, in exponents, when do you add exponents? When they are getting multiplied, right? You remember that?
Yeah.
A to the power of m times a to the power of n is what? A to the power of m plus n. You see that, correct?
Yeah. Mm-hmm.
So here it is like these powers are being added. That means it should be inverse. In inverse, it gets multiplied, right? So it'll be 7 times 5, 35. So 8 minus 35 will be your answer for this question.
Oh, okay. So you just multiply the exponents?
Yeah, because they add in it. If it is subtract, then you subtract. So we'll learn this formula in the next chapter. Is it okay?
Okay.
Anyway, you got an idea, right?
Yeah.
Okay. Now, let's do some other question.
Can we
Let's
do 22?
22, let's do 20. Sure. Graph each of the following functions. Graph each function and its inverse, right? Okay. So 3 log x plus 6. How will you do this? So log function, it is base 10, right? So basically, let me sketch the log function first. Log function is kind of like this. Base is, this is this, right? Important property for, I'm just sketching the function, which is log x. Is that okay? So that means this point here is at 1. And then we also know that since the base is 10, the value will be at 10 will be 1, correct? Log 10 of 10 will be 1, correct?
Yeah.
And it will have a -1 value for 110. Correct? 10 to the power of -1 will be 1 over 10. Is that correct? Now,
Yeah.
so we have these critical points. So let me write down the critical points as 1 over 10, which will give us -1. And the second one is at 1, I have 0. And the third one, at 10, I have 1, correct?
Yeah.
What is the transformation? We are doing part A. We have to multiply the y values by 3. So the transformation is, if I have x and y point, in that case, the x value subtract 6, right? And the y values multiply by 3. Clear?
Yeah.
Now, that means first is vertical asymptote, which is at x equals to 0, right? It will move 6 units left. So we'll have a vertical asymptote, which will be here now, which will be at x equals to -6, correct? So we got the vertical asymptote. Now the point 1, let's do the transformations for all the 3 points. So we get 3 points. So first point, x -6. So do 1 by 10 -6, what do you get?
1 over 10.
So yeah, 1/10 less -6, right? So 5.
-5.9.
Yeah. Yeah, this is 0.1. You can say -5.9. And the y value multiply by 3. -3. Is it okay? -1 becomes -6. So you got this point. -5.9 is very close to -6, and -3 is somewhere here, right? So you get 1 point here. You get the idea?
Yeah.
Next one is -6 from 1. That will give you -5, and 0 remains there, right? So at -5, we have a 0 now. So -5 gives me a 0. Is it okay? Somewhere close?
Yeah.
And the third point, when I do -6 from 10, I get 4, right? And to 3 for 1. So we get 4 and 3, right? So at 4, we have 3. So let me just connect these points. Where this point here will be at 4, I have the value 3. Is it okay? So that is how we are going to sketch the logarithmic function as in 22a using the transformation properties. Is that clear to you?
Yeah.
Easy.
Can we do also question E?
Yes, why not? Let me clear this. So that is exponential function transformation. Base is 3. So basically, let me do it with the, here is the graph of the exponential function. Critical point being this point, which will be at 1, right? We are doing 3 to the power of x. Is it okay? So, and these are 2 critical points. At -1, I have 1 over 3. And at 1, I have the value as 3. Is it okay? Now, you want which one? You want E. So you want twice. So the transformation is that y values get multiplied by 2, and it has been translated 2 unit left, right?
Yeah.
The point xy is actually transformed, and we get the x values, which are -2 from the initial value, and the y values are twice. So if I have to transform, then this particular point in the center, which is at 1, will go 2 units left, right? Somewhere here. And get multiplied by 2. So instead of 1, this will be at 2. So it will be here, right? Do you see that? You can write down the points and transformation. That'll be better for you. Let's read it. I mean, write down the points. So we have these points as -1, 1 over 3. And then next point is at 0, we have 1. And then at 3, we have 1, correct? Oh, sorry, 1 we have 3. 1 we have 3. Wait. Add 1 we have 3, correct?
Yeah.
Now, let's apply the transformation. X minus 2. We'll make these points as minus 1 minus 2 is minus 3. Let's do this. And this will be minus 2. And this will be minus 1. Is it clear, these 3 points? Y values, multiply them by 2. So 2 over 3. Y value will be 2. And Y value will be 6, correct? So plot these points and then sketch your graph.
So it's just applying the different like vertical transformation, multiplying them, and then to the original parent function to get them. Yeah. Okay.
Perfect. So you have understood everything?
Yeah. I also wanted to do, I think we passed some word problems.
Sure, we'll do that. No problems.
Like ones like this over here.
Any problem. Take any problem.
Maybe this one, 15.
Okay. Read the question.
The astronomer Johannes Kepler, 1571 to 1630, determined that the time, d, in days, for a planet to revolve around the sun is related to the planet's average distance from the sun, k, in millions of kilometers. This relation is defined by the equation log d equals 3 over 2 log k minus 0.7. Verify that Kepler's equation gives a good approximation of the time it takes for Earth to revolve around the sun if Earth is about 150
so many thousand kilometers from the sun, correct?
Yeah.
So now here we know distance, right? So here the distance k, average distance of the sun, k in millions of kilometers. So how many millions it is?
150.
150 million. So just put 150 there and find d, right? So let's calculate. So we have log of d. We want number of days. 3 by 2 log of 150 minus 0.7. Check. Do you get 365? Not 10 to the power of 365. Okay, we'll find d, right? First check this. What is the right hand side equal to? 3 by 2 log of 150 minus 0.7 is how much for you?
1 second. Log 50 minus 0. Negative 0.01.
Did you take minus 0.7 also from it?
Yeah.
Okay, let me do it again. First to log 150. So log 150 equals to multiply by 3 by 2. So times 3 divided by 2. And then take away 0.7 minus 0.7. And you get 2.5641.
Oh, okay. I just put the whole thing in the calculator.
Yeah, that's why you got it wrong. So 5641. And now d is 10 to the power of 2.5641. So don't erase the value. Just keep that value and do 10 exponent your answer and you get your answer 366.5. You see that? Because log of d is that value of 2.5641 and d should be base is 10 to the power of 2.5641, which is 366.55.
So you just 10 to the power of the number we got, and that's the answer?
Yes, because log d is that much, right? Not d. We have to find what d is. So log of d is 2.56. D will be 10 to the power of 2.56, which gives you the number of days in a year, correct? So that is how you have to do it. You can take the next question also, question number 16.
Use Kepler's equation from question 15 to estimate the period of revolution of each of the following planets about the sun, given its distance from the sun.
Correct. So just plug it in and find D, right? So you plug it in, get the value, then 10 to the power of that will be number of days. Is that clear?
Yeah, so the number to that, like for example, question part A, 2,854 is the K value.
Correct.
Yeah, so you make that, you get that, and then you do base 10 to the power of that, and then you get the answer.
Perfect. So we've done almost everything in this chapter. I hope it is clear to us, right? I'll upload the video. You can watch it just as a review. That'll be good for you. Okay?
Yeah.
So we can end our class here. Can you review or summarize what did we learn today? Can you summarize what did we learn today?
Yeah, so today we focused on like the several equations that we learned today, and then how to apply them through word problems, how to evaluate them, how to estimate, and then also turning them into a graph.
Yeah, right. Perfect. So I hope everything is good. So try to do these questions on your own. If there's any difficulty, you can post those questions to me, right? Send the message or the email. I'll reply back to you. And let's look forward for the next class now.
Okay.
Yes.